Okay, start.
Alright, hello, welcome to lecture 10. We have another only 45-minute class because it's very cold in Maryland. Very cold. Very cold in this room. Okay, can you get the door? Emma, can you get the door? Can you guys take out your sketching derivatives worksheet? We're going to super fast go over it.
Wait, no.
We're going to spend very little time.
May use the restroom.
Okay, like fast. Take it out, and let's start comparing it to the person next to you. I feel like we mostly did the front.
No, we only did the first one.
Okay, whatever. I'm going to pretend that we did all the front together, so let's flip to the back, and let's see if everyone agrees. Well, I disagree strongly. Talk, discuss.
Disagree strongly.
That's really careful. This is difficult. It's not an option.
So the same line. So we
You finished?
Yeah.
You know what's name? No. You'll figure it out.
Because like a tangent line to a line is the same line.
Yeah.
You have
So
to
you're
draw
changing mine?
the second derivative.
Everyone at the table agrees?
Take the derivative and then
I agree with that.
I see how it looks.
where's my red?
Who's Sydney?
I'm Sydney. Wait, what?
Does everyone at the table agree? Everyone at the table agree with everything? Yes, that's wrong.
And then.
Are you understanding what you're coming from math help?
Oh wait,
So draw the second derivative.
No, I'm going to talk about that in a second.
So we don't have to have two.
Okay, flip to the back.
So I think I'm on here.
That's wrong. That's wrong. You didn't do the back. Come on, man. This is important. Oh, I see. Okay. Any outstanding questions? Going once.
I have a question.
Yeah.
Can I have the new paper?
No, you need to get it together. All right. So, good. So the actual directions on this worksheet, I'm not sure if you read them or not. The actual directions on this worksheet were saying something about the second derivative, whatever that is. What is the second derivative?
The derivative of the derivative.
Yeah. Are you just guessing? Or are you ready
Well,
into the book or something?
what else is
It is intuitive, and I agree, and that is also the correct answer. So what is a second derivative in general? Just like you said, it is the derivative of the derivative. So for example, if I give you some function like f of x equals x to the fourth, say, and ask you for the derivative of this function, what is the derivative of this function?
4x cubed.
4x cubed. The so-called second derivative has notation f double prime. Seems like a reasonable piece of notation. And what is the second derivative in this case?
12x squared.
Yeah, it's just 12x squared. Okay, so far, simple, easy, nothing really to talk about. All right, well that was kind of a lame math teacher way of talking about the second derivative. What you should really be constantly asking is, what does it mean, man? What does it mean? Can someone tell me, can someone come up with some sort of interpretation of the second derivative, what it means, what it's about, why we would care about this, why we might use this? Think. What are we doing here? What's the whole point of this life that we're in?
I don't know.
To avoid work.
Emma, what's the whole point of calculus anyway?
Oh, calculus, measure change.
Yeah, to measure change. Yeah, okay.
Hard to measure the rate of change, like the rate of change at which it is changing.
Oh yeah, okay, so that's the thing. She's like, yeah, if calculus, or at least if differentiation is about the rate that something is changing, then the second derivative is like the rate of change of the rate of change. I love that answer, it's brilliant. So she's saying the second derivative measures the rate at which a rate is changing. Yeah, okay. More. Why are you making that face?
I mean, like, what? Okay.
Yes,
Isn't that
Calvin.
related to that thing where you like showed if you like did the weird like seeing how much increase each time in like a quadratic or something?
It is related to that. Yeah, yeah. We talked about, as we talked about on the day that we did the power rule, the second finite differences is kind of like the rate of change of the rate of change. I agree. More, Eo.
It's like acceleration.
Yeah, how about physics? How about the whole reason why Newton invented calculus to begin with, according to the history that I've presented to you, whether it's true or not, that was the entire motivation for all of this, was physics. And we have talked about these functions already. Let's not forget about them. We should be thinking about them constantly, because it is the motivation for everything that we do. So suppose we have some position versus time curve, and we now know that when we take the derivative of a position versus time curve, we get speed. Although we're going to be big boys and girls now and not say speed anymore. We're going to use a more precise word. Yeah, the velocity. So, so let's take a position function. So let s of t be some kind of position function. And we are going to allow this function to be, keeping things simple for now, we're going to allow this function to be a positive or negative number. Okay, so that kind of indicates that the position of an object can be described with a single number. In other words, maybe I just have someone, running along a line or whatever, and that person may be at -2, or that person may be at 5, etc. Does that seem reasonable for now?
Yeah.
Okay. So think of s as being a function which takes as an input a time and output a single number which describes position. Good so far? All right, well then, what is s prime of t? It is the rate of change of the position. It's the rate at which the position is changing, and that is, as you guys said, velocity. And not only is that velocity, but literally we will define velocity to be the derivative of the position function. When you take a calculus-based physics class, which all serious physics classes are calculus-based, they will give you a position function, and the very concept of velocity will be just defined as a derivative. Yes, Bucius?
Why does it say s of t equals positive?
Oh, because I am tired and I wrote the wrong word. That should say position. Thank you. Okay, and now get to the actual thing that we're talking about. The second derivative. What is s double prime? Yeah, well, it is just the derivative of the velocity. In other words, it is the rate at which the velocity is changing.
Oh, I did.
And the rate at which the velocity is changing, loosely speaking, the rate at which your speed is changing, that is just acceleration. Follow? Any questions, comments? Okay, so that's cool. Can we keep going? Can I take a third derivative?
Yes.
I guess.
Yeah, I guess so. The third derivative would be what, in your own words?
The rate of change
The
of the acceleration.
rate of change of the acceleration, yeah. So, there's even a word for this, we call this the jerk. And that's the idea of, like, if you're in a car and someone accelerates rapidly, then you might just like, and you just kind of drop your coffee or whatever. And all of these things are kind of interesting, right? So this is something that you might measure. Well, you might be interested in that. I guess I had some funny jokes yesterday, but I don't know, whatever. Nothing with that.
What?
Good. You can keep going with this. It quickly gets out of control. There are some more like nerd terms for what happens when you take the fourth derivative. By the way, there's like a symbol for this. We go like, so that's like the derivative of the jerk. So that's like at this point I'd lose it. I can't. I don't think I have the cognitive powers to distinguish between the rate of change of the acceleration and the rate of change of the rate of change of the acceleration. If you concoct a long, complicated, weird story about that, I don't know. All right, Eob, that's what it all means. The directions on this paper, which I would now like you to execute, not in class but later for homework, is when you're 100% sure that your first derivative is right, which that involves you talking to other people and possibly me. That needs to be fixed.
What?
That needs to be fixed. Some things going on here are very strange. You need to come to math up. Everyone needs to come to math up every single day. then when you're 100% sure, that's wrong. When you're 100% sure that your first derivative is correct, please go over it in blue colored pencil or marker or whatever. And now sketch on the same axes the second derivative. And then when you're 100% sure, you'll go into red. Sorry, what? How do you know when it's right? Talk to enough different people. And if you all agree, then you're all probably right. And if you all have different things, then you argue about it until you are all convinced. And there's consensus. Because there's only one right answer, because it's math. Yes, Calvin, question?
What if there's just like one person who refuses to believe all the others?
That's like 12 Angry Men.
Okay, good. So then you go to math. All right. In addition to this, oh, I forgot to tell someone to do this. Would somebody be willing to, in nice handwriting, do one of the things you had to do for homework was to come up with the derivative of cosine? Would you on the backboard? While she's doing that, can we just talk? Well, actually, let's do something. While she's doing that, let's do something else. What should we do? Let's talk about this function. Really important function. This really important function is, well, actually, let's just kind of review. Raymond, what do I currently know how to take the derivative of? Let's get the full list. Polynomials, check. Wait, we're doing cosine though, right? Yeah. Sydney? That's what I wanted you to put on the board.
Wait,
Cosine was wasn't that your first homework problem? Was
okay.
derive the formula of the derivative of cosine?
Yeah.
So sorry, Raymond, polynomials?
Some trig function.
Some trig function, specifically sine and cosine, and that's about it. What else? More people say things?
Maybe we can get a tangent from that.
Maybe we can get tangent, but not yet.
I don't know how.
Let's talk about what we do. Let's talk about what we can do now. What can we do now? Polynomials,
Addition.
trig functions, addition. That's important, right? If I know how to take the derivative of two functions, then I can take the derivative of their sum. So I can do sine plus a polynomial. Do I know products? I don't.
No,
No, by constant.
And I know constants. I think that's it, right? I think that's it. I think I can do I can do polynomials. I can do a constant times anything, and I can do sine and I can do cosine. All right, here comes our next important function, and that is the derivative of e to the x. Whoa. Arun, I think we should do some review of e to the x first. Shall we do some review? What do you know about this number e? It's like some limit or something. Yeah, specifically 2.7. Yeah. You did this in pre-calc C and also in pre-calc B, so we should be experts at this.
The ratio n goes to infinity of like 1.
1 plus 1 over 2n.
Yeah, so just very, very quickly, here is how the concept of E was first presented to you, I think. You took some, we had this formula which we derived for compound interest. We did this very carefully as like a kind of like a geometric sequence problem, right, Mateo? Yeah, and the problem said that if you are given principal P and you deposit it in a bank account and then do not touch it for T years, and you do this at interest rate R, then via a long kind of algebra 2-ish derivation, we find that the amount of money in the bank T years later, assuming that I'm compounding n times per year, is P times 1 plus R rent to the nt. Cool? And then we did this thing, you guys remember what we did? We like made everything 1.
Yeah.
Like we took $1, I just did this in functions yesterday. We took $1 and we invest $1 for 1 year and at 100% interest rate. So R is 1. Is this ringing a bell? Can you just vigorous head nods? Yeah. And then we made a chart and we said, okay, what happens if you compound 1 time per year? What effect does that have on the final result? Common sense answer? 2. Yeah, of course, because compounding 1 time per year, if we're only investing for 1 year, it's essentially like saying not compounding at all. If we're going to win 100% interest on $1, at the end of the year we should have $2. Yeah, yeah? Yeah. Okay, and then if instead we compound twice per year, well, then I can use the formula, and the formula says, well, I take my $1, I go 1 plus R, which is 1, over the number of time period compounding, which is 2, times 2 times 1, and that turns out to be,
0.25.
yeah, just 3/2 squared, that's 9/4, that's $2.25. So I end up with $2.25, and I'm very impressed, and I'm so happy, and thus I will try to compound more often, or go, whatever it is, go to drive to the bank and take my mustache out of the glove compartment more often than twice a year. That will be incomprehensible to anyone in this class. What happens if we compound more often, like n equals 4? Yeah, then we get 1 plus 1/4 to the 4th, and then that turns out to be like, I can't remember, like 240 or something, or 250 or something. I'm just making up numbers. And so then what happens is, if we do this infinitely often, so if we let n go to infinity, then what I have is this expression 1 plus 1 over n to the n, and what we end up with is $e. So, definition of E. Definition, E is a limit. It is defined to be a limit. It is the limit as n goes to infinity of 1 plus 1 over n to the n. Is everyone cool with that? It's like a definition of E. All right. So happy about that. All right. There is an alternative definition of E, and the alternative definition involves just rewriting this slightly differently with a limit switchy. So let's define some new variable like a be 1 over n. So if I define a to be 1 over n, can you rewrite that limit in terms of a's, thus producing an alternative definition of E? Please do that now. Alright, are you done basically? So since a is 1 over n, then it's just a fact that as n goes to infinity, a goes to 0, or 0 plus to be exact. So E could alternatively be defined as, every time I see an n, I'm just going to replace it with an a, so this is 1 plus a to the 1 over a. Yeah? Are we cut off? Heads in the way? Yeah. And thus, I will write this as the limit as a goes to 0. Okay, so 0 plus, it ends up being the same either way, but okay. Or maybe not, maybe I should do 0 plus. There it is, that's certainly right. All right, so these are two totally equivalent definitions of E. Is everyone satisfied? All right, back, should we take a pause and check out what's on the backboard? I think we should, because it's quite beautiful. So what we did last class at the very end, as we were running out of time, was we took the derivative of sine and we showed the derivative of sine was cosine. What you had to do for homework was to come up with the formula for the derivative of cosine. And okay, they kind of told you what the formula was, thus stealing some of your excitement. But of course, we could do this the same way we did it in class, which is to conjecture what we think the derivative should be. So we have like 1, -1. What does cosine look like? Cosine has this shape. And so, kind of a terrible cosine. So if we want to try to sketch the derivative of cosine, I think it's always a good idea to try to sketch the derivative of a function before trying to do the algebra. So what should this derivative be? Well, at 0, what's the derivative of cosine? 0, because tangent line flat. At pi over 2, what should the derivative of cosine be? -1. Yeah, and that's just kind of, and I sort of know that because we already did this out with the sine function. Since cosine is just sine shifted. That's a tongue twister. Cosine is just sine shifted. Okay, so what? We have a short class today, so you just tell me to stop going around. So if I look for the derivative of at pi of cosine, it's 0 again. Now the derivative is 1, and now the derivative is back to being 0. Okay, so with just a little bit of effort, I have sketched a conjecture for what I think the derivative of cosine should be. And the answer is that looks a lot to me like negative sine. And so I conjecture that the derivative of cosine is negative sine. And now we have a proof of this. So we do it the only way we know how, using the definition of the derivative. So the derivative of cosine is the limit as h equals to 0 of cosine x plus h minus cosine x over h. And just like we did in class, this was your opportunity to sort of practice it again. We expand out the cosine using the cosine of a sum formula. Boom, boom. And now she does a whole bunch of algebra all at once, splitting this limit up into kind of like taking the first and third term on the one hand and the second term on the other hand. Sorry, I'm making your thing kind of messy now. But so what we get is the limit is splitting up the limit into the limit as h goes to 0 of negative sine x sine h over h, and the limit as h goes to 0 of cosine x cosine h minus cosine x over h. Well, now I can take negative sine x just like straight out of the limit, and sine h over h goes to 1. So this whole limit is going to go to negative sine x, and then for this one, she factors a cosine out, and now we have this famous limit that we've heard of before, which goes to 0. So the answer is negative sine x. Cool? Okay. Class ended before I had a chance to do my normal melodramatic kind of discussion of this, but like, use this. It is quite incredible that the derivative of cosine is negative sine, for example. What this is really saying, I mean, it's easy to just be like, oh yeah, ho-hum, another formula. No, not just another formula. This is telling me, right, because the derivative is the rate at which the function is changing.
Yes.
In other words, if I take this cosine function, at every single point of this cosine function, at any given moment, if I would like to know at what rate that function is changing, which is just the slope of the tangent line,
Yes.
the answer is, it's the value of whatever the negative sine function is. It's like amazing. You thought,
No.
I got one person to feel like that's like, it's like kind of incredible, right? We already knew all these relationships between sine and cosine. They're co-functions. The sine of an angle is the cosine of a complementary angle, so that they're shifted over each other. They also have the Pythagorean relationship. They also, each one of these functions describes the rate at which the other one is changing, which is also saying something kind of deep, right? Since negative sine is always between negative 1 and 1, the rate of change of the cosine function is it's never changing by faster than negative 1 over 1. It's never changing faster than 1. Okay, you guys don't seem impressed, so let's waste like another minute of time. Take this function f of x equals cosine. What is, so the derivative we just found was negative sine x. Okay, but now that we know some things, we could just keep going, right? What's the second derivative?
The negative cosine x?
The derivative of this would be, well, the derivative of sine is cosine, so it would be negative cosine. Whoa!
Wait.
Cosine is a function whose second derivative is the opposite of itself.
Oh my god.
In other words, at any given moment, the rate of change of the rate of change of cosine is negative cosine. And it gets better, because what is the third derivative?
Sine.
It just becomes sine. And the fourth derivative is
Cosine.
back to being cosine. Alright, so the rate of change of the rate of change of the rate of change of cosine is cosine. In other words, the cosine function is somehow telling the sine function how fast to grow. At any given second, the cosine function asks, hey man, what should I do next? And the negative sine function tells it exactly what to do next. Yet the sine function is following the directions of the negative cosine function, which is in turn following the directions of the cosine function, which is in turn following the directions of the cosine. It's kind of incredible. Yes?
So there's like no end to this loop.
There's no end to the awesomeness of differentiation. All right, good. That was the homework problem. Back up here, we have now reviewed the definition of E, which we experienced in pre-calculus. It is now time to take the derivative of e to the x. Go.
Take the derivative of by writing. Wouldn't it be 0?
35 minutes.
Yeah. Yeah. We had an hour-long class, not a 45-minute class. I think. Because we start at 1:10, right?
Oh yeah.
I'm so confused.
It's an hour class.
Why is this class an hour? Just because?
Like like the first class is like 45, and then another one's like 1 hour and 5.
What's that about?
It's just weird.
Because
MCPS can't. No, it's much.
Oh.
Because you want to have a bunch of like
I see, so you can't have one. That's so weird. Okay, so we actually have more time. We have a lot of time-ish.
We have to like
Perfect.
You're like 10
Great.
minutes extra. I guess
10 minutes is like
enough to, yeah.
How's it going?
Badly.
Good. That means you have a high opportunity for learning.
We haven't learned this yet. That's even worse.
What is anything to do?
Like we haven't gotten to that point where you like learn something.
Are you writing things?
I'm writing.
Yeah, well, right.
Actually, yes, you can.
I don't know what.
Wait, what?
So I got probably pretty cool.
Wouldn't it just be equal to 1 over A?
Yeah, but you can just those the h times e to the x, and you can pull out.
Easier for you to like
And e to the h on purpose.
Yes.
But that's what they don't derivative at a specific
No, it's not because x goes to a.
X goes to
X
A.
minus e to
I'm gonna do that.
It'd be 1 plus e.
Wait, you get e to the x times e.
No.
And then this
I'm
is like
talking out loud. I'm sorry. So it'd be like 1 plus a. Oh yeah, you're right. It is the x
No,
plus h over
that's
a.
not nice. It's not nice
How
at
is it
all.
right?
But we don't have anything.
But can you just like plug that?
No, but that's less nice
We're
because
using
now we have
formulas.
like
But
2
that's
x.
the formula.
Sometimes you want more.
Wait, it's not just
I don't
e,
know
is
why
it just
we're
that?
going further into this. This might be that time.
No, I think we want the powers more than. We can like bring the e down because e to the x times e to the
We don't even have a formula
we can,
system
like,
for x, so I don't even know how we do
Yeah,
that.
no, that's
totally the way to
No,
go.
I-
That's totally the way to go.
No, it's like 1, you're just going to be 1 minus 0.
Oh, and then.
Wait, I'm really confused
Got
about
it.
like what we do.
Yeah, me too. Yeah.
E to
I don't know what we're supposed to do. I mean, here's what I got. That's just the definition of the derivative. Who got this far? Hopefully everybody, because it's just nothing. I mean, can you think of anything else to do?
Yeah.
There's about 1 or 2 obvious things to do.
1 e to the x.
Split it up. Yeah, I mean, it's the same thing. It's the same thing over and over again, right? When we do the power rule, and we had x to the we had x plus h to the n. What did we do?
I don't know.
Expanded it out via the binomial theorem. Nod, please. When we were taking the derivative of sine, and we had sine of x plus h, what did we do? Expanded it out using the form of the sine of a sum. This is the easiest one yet, right? Here we just do the obvious thing, which is to rewrite this as the limit as h goes to 0 of e to the x, e to the h, minus e to the x over h. Okay, not really impressed yet. More? There's another pretty obvious thing to do. Yeah, factor. So if we factor, we get the limit as h goes to 0 of e to the x times e to the h minus 1 over h. Okay. I'm pretty stuck. Raise your hand for I'm pretty stuck now. I mean, I was hoping everyone would get this far and then just be really, really stuck. Anything else? Yeah, other things? Yeah?
I was thinking of 2 different things, like either try to multiply by conjugate or try to do difference of squares, but I don't know if any of those.
Yeah, I don't think so. It was about 1, yes, me?
Can you somehow apply that thing on the bottom where a goes to 0?
Yeah, okay, so I'm going to get to that in a second, but yeah, ultimately yes. But even maybe just a quick thing, yeah, a quick thing?
Maybe split up the limits. Like the limit is h goes to 0.
No, we can't.
Over h.
Well, yeah, we can definitely do that, right? I mean, we can, because, again, this is this move which we've done twice already now, so I'm going to do it for a 3rd time. and then some people are a little bit uneasy about this, but you know, get over it. I'm taking that I have x's and h's here. You need to keep track of what's the variable. With respect to this expression, since we're taking the limit as h goes to 0, you know, h is the variable which is changing, right? X is not changing as far as this limit's concerned. So x might as well be a constant with respect to this limit. So I can just take e to the x right out of this thing. Is everyone cool with that?
Can we
What's
only
up?
do that if e to the h minus 1 over h is, if the limit of that is
Oh,
defined?
assuming that that limit exists? Yeah, that's true.
But,
yeah.
So we can just do that, and then if it doesn't exist,
If it
then
doesn't
already
exist later,
continues
but
to be,
it exists, yeah, exactly, exactly. Okay, so good work, class / me. I think we have gotten this far. I now need only figure out what this limit is, and then I'm done, right? Okay. There's so many things to say right now. We could have a 90-minute class just based on discussion at this exact moment. Roddy Fleischman is worried that maybe this limit doesn't exist. Okay, by the way, I'll just say that it does exist. Just trust me for a moment. Okay, yeah. It's some kind of number. Let's just call it like k or something for the moment. All right. If this is just some number k, something brilliant and amazing has already happened.
What?
Even though I haven't finished the problem yet. Yeah, fair enough.
The derivative stuff is like a constant and stuff, and like e to the x is the thing. Derivative.
It's like,
That's the most terrible explanation ever, but yeah, I agree with you. Yeah, look, if I just temporarily call this k, I have just shown that the derivative of e to the x is k times e to the x. What? What? In other words, the rate at which this exponential function is changing is also another exponential function.
Oh boy.
Whoa. In fact, this is an incredible thing that you sort of already knew, maybe depending on how much Giles talked about this last year. Exponential functions increase exponentially, right?
Wait.
Yeah, so you kind of knew that already, right? Because it gets discussed, but not really. And in fact, something that happens a lot is that people abuse the language, and people all the time, especially people who don't know what the hell they're talking about, say things like, oh, such and such is increasing exponentially, right? But actually, probably what they really mean is that an exponential function best fits that data, right? And for example, if someone says something is increasing quadratically, do they really mean that, or do they mean that a quadratic function best fits the data? Like sometimes you'll find people misusing those terms, right? If something is quadratic, then it's increasing linearly, et cetera, et cetera. But if you notice with exponential functions, sometimes people just say, oh, it's increasing exponentially. They are technically correct because exponential functions do increase at an exponential rate. This is what makes this makes these functions so incredible, right? If you give me some polynomial in degree 100, the rate at which